all the way to the code. Might take tomorrow.
Okay, so I think we left off, we were talking about momentum, right? So we're looking at linear momentum, that was the topic. So let's look at 7.3. We're going to look at example 7.3. I think that's on page 171, yeah. So in example 7.3 you have two railroad cars, and here's what they say. So they say a 10,000 kilogram railroad car traveling at a speed of 24 meters per second strikes another one that's identical and it's at rest. If the cars lock together as a result of this collision, what's their common speed afterwards? Okay, so that's the problem. So let's see, I need to draw a couple cars, right? So before the collision we have car A and we have car B is just sitting there. And after the collision they're kind of just one mass because they're like sitting up next to each other, right? So we've got before and after the collision. So car A is moving forward, car B is at rest, and then afterwards I should draw this vector probably a little bit less because won't they probably be moving at a little bit less speed after that collision happens?
Yes.
Yeah, okay, so I'm going to put like an equals in there, it's kind of what's happening. Alright, so we're going to use conservation of linear momentum to do this problem. So, did they give us some masses and stuff? I think they did. Yeah. Let's just keep in symbols for now. So what's the momentum of car A? It would be its mass times its velocity. Okay, so that plus the momentum of B would be its mass times its velocity. And since linear momentum is conserved, you can say that's equal to what over here? The mass of that thing. What's the mass of that thing?
Both of them together.
Mass of A plus mass of B. All that mass times
The original
its velocity. If you want to say AB or B prime or something, you know, you can put whatever you want on there. Does that make sense? So those have to be equal, and that's because of that conservation law, because we can't lose momentum in this process. Does that make sense? Okay. So I think we just need to solve for what? What were we trying to find? Remember, we always should put that at the beginning of the problem. Maybe even before doing this, I should have put, what were we trying to find? Velocity of this?
No.
This? I'm trying to find this guy's velocity, right? So I probably should have specified that at the very beginning. So we need to solve this equation for that. Isn't that going to be pretty easy? Don't I just go VAB equals and divide? Isn't that it? Just got to divide that over and you're done. What's nice, this thing was supposed to be at rest, so this part goes to, because that velocity is 0, this guy is going to go to 0. So that's gone. And do we have the other things? So let's see, mass of A, didn't they say 12? What was it? Help me out.
10,000 kilogram.
10,000? Oh, okay. And its velocity was?
24 meters per second.
So we're good on our units, and then we've got 10,000 plus mass of B, so 20,000 on the bottom. And that's your velocity, which, what's the book say it is?
12. Exactly.
12 meters per second. That makes sense because it's less. We were thinking it was going to be less after they collided. So that makes sense. There you go. So there's a conservation of momentum problem. I like that one.
Why did you put the masses on the bottom?
Divide.
Oh, right, okay. Got it.
Yep.
Where's the velocity? Oh, velocity.
Okay. Okay. You got a question? Ask it. Okay, I thought we'd read these top two paragraphs, so I'm just going to read them out loud. You guys can follow along in 172. There's not much in here we need to read, but this is nice. So in 172 it says, as long as no external forces act on our chosen system, conservation of momentum is valid. In the real world, external forces do act, like friction, gravity acting on a baseball, and so forth. So it may seem that conservation of momentum cannot be applied, or can it? In a collision, which is mainly what you're going to be studying in this section, when things collide like pool balls or something, the force each object exerts on the other the force is exerted only over a very brief time interval and is very strong. For instance, when a racket hits a tennis ball, both before and after the collision, the ball moves as a projectile under the action of gravity and air resistance. During the brief time of the collision, however, when the racket hits the ball, external forces are insignificant compared to the collisional forces that the racket and ball exert on each other. Does that make sense? So you're kind of ignoring those really tiny, insignificant other forces. The main thing that's happening is the force of the collision between the objects. I think that's the key here. And another key, which I have highlighted, is the law of conservation of momentum is particularly useful when we are dealing with fairly simple systems such as colliding objects and certain types of explosions. The rest of that paragraph might also be useful for you guys to read. So momentum is applied in situations where you have two objects colliding, and you look at what's happening before the collision and what's happening after the collision. That's a really common application of it, because the friction involved is so negligible that you don't really have to worry about it, and you can still solve your problem, okay? And it also said what other situation? Things like explosions, and it goes on to talk a little bit more about that. But my point is, if you have objects that are colliding, you probably want to apply momentum, okay, rather than like forces, kinematics, and some of the other stuff that we'll study or have studied, okay? So we're going to talk about a couple different types of collision situations today. Let's look at example 4. Example 4 is about a rifle recoiling. I think it's really simple. Can you guys read it and just look through it real quick? I'm not going to go through that one. Just see if you can skim it and see the answer. It's pretty easy. Do we have any questions on this one? I think it's just like that other one, but why are those both 0 in the momentum before part?
Yeah, the bullet got
The bullet and the, what else? The rifle are both still, so those velocities are 0. And what are we trying to solve for here? The velocity of the gun, because they asked us for what? Recoil. Well, isn't that how fast the gun is moving when you shoot it? So you've got two things there. You've got the velocity of the bullet and you've got the velocity of the recoil. Did they give us the bullet? I think they did. Yeah, they said the bullet has a speed of 620, so you just solve for the other one. So that's another one that's pretty simple. Let's look at example 7.5.